Hey there, chemists. It's time to check in and just recap a couple of the reactions that we've done so far. We've learned two related to alkyl halides, the SN2 and the E2. And on your screen, I just have an example of each. Remember, the SN2 is when you have a very unhindered alkyl halide, something like a primary alkyl halide. And the E2 is when you have a much more crowded, sterically crowded halide, like that tertiary one right below it. And to remember how the mechanism works, the SN2 is when you have a good nucleophile, so there's a phosphid anion, that's a large, not very electronegative phosphorus atom. It's willing to give up its electrons and form a bond with the carbon, so I could draw an arrow from the phosphorus to the carbon attached to the bromine and show the bromine leaving, and that's how I get my substitution product. As opposed to an E2 reaction, which is when I have a much more hindered, like a tertiary halide. I got a strong base. Oxygen anion's a great base. It'll take away one of the beta hydrogens. There's several of them, aren't there? There's two right there. There's two others right there. There's actually three more down there on the methyl. Those are all beta H's, and all of them have the ability to be, or enough of them have the ability to be anti to the leaving group, so I have a possibility of an alkene anywhere. But this is a small base, so we're going to get the less substituted, we're going to get the more substituted alkene by taking away one of the less abundant H's. So if I wanted to show arrows for this, the methoxide would take one of those H's, the CH bond would become a CC pi bond, and the bromide would leave. So that's what's up with primaries and methyls, and with tertiaries. What about secondary halides? We just kind of skipped over those, and I did it intentionally, because secondary halides really can do both. Now it depends on what we're using as the other reactant, in other words, the nucleophile or the base. So when we have a secondary halide, it's quite competitive to do SN2s or E2s. And all you have to do is look at the other reagent. And if you've decided that it's a nucleophile, in other words, a larger atom, not very electronegative, but still negatively charged, good chance you will have an SN2 reaction. So here I have iodide. Remember, this is Na plus and I minus. And I'm being told that this is an SN2 reaction, and I want to figure out the product. So I find my electrophilic carbon attached to the bromine, my nucleophilic iodide. I draw an arrow from the iodide to the carbon attached to the bromine, and the bromine leaves. All those carbons are along for the ride. 2, 4, 6, and 7. And now I have an iodide attached to that carbon where the bromine used to be. Now remember, the SN2 occurs with inversion. So it's not until we get to secondary halides that we see this inversion of stereochemistry. So whatever the asymmetry was here, it's inverted. It looks like that's going to be an R asymmetric carbon in the beginning, and it became S. Double check with your right and left hand roll. Yep, in the beginning, H coming out at you, bromine, followed by alkyl, followed by methyl, that's R. And then on the right-hand side, we get to an S. So your stereocenter has inverted. What about the one right below it? Well, find the carbon attached to the leaving group. We're being told this is an SN2, so that's my electrophilic spot. What's my nucleophilic spot? It's the sulfur. There's lone pairs on that sulfur atom. Again, if you're sometimes given the reagent as an ionic compound, remind yourself that there's charges there, and you've got a spectator ion. You'll never have just SH anion sitting in a laboratory. It's always got to have some counter ion with it, but it's not doing anything chemically for us other than balancing the charge. So draw an arrow from the sulfur to the carbon with the bromine and draw the bromine leaving. And then what's your product? We have a 6-membered ring. We have this methyl up here, along for the ride. Now there's still inversion of stereochemistry at this center. Even though this is an achiral molecule, we do get a specific stereochemical relationship. And in this case, the sulfur is attached to the carbon where the bromine is, where the bromine used to be, and it's going into your page. We do not get the other diastereomer where this would be coming out of the page. That's not what's formed. So this is a diastereoselective reaction because that other methyl has desymmetrized the molecule. Okay, now what about E2 reactions? Well, we can still do an E2 on a secondary halide, but here what we're looking for are things that are strong bases. Remember we said in the previous lesson, look for things like oxygen anions and nitrogen anions. Those are going to be red flags for most likely an E2. And then we have to also pay attention to things like the anti-periplanar restriction, and is it a big base to give us the non-Zaitsev, or is it a small base to give us the Zaitsev product? This is a small base, methoxide. Notice sometimes they'll put a solvent below the arrow. That's just common because usually you have a solvent in your reaction. It's quite often the conjugate acid of whatever your base is. So for our purposes, it's just there. How do we figure out the product? Well, we're going to lose one of the beta hydrogens. I'm going to draw in the beta hydrogens on my picture. I've got one right there, and I've got 3 more out there. So I'm going to lose the bromine, and I'm going to lose, this is a small base, so I'm going to lose an H from the spot where there are fewer H's, which is that one, and then we get a new pi bond in between. Now notice the H and the bromine are already drawn in an anti-relationship, so I get a product that looks like this, with an alkene right there, and then a methyl going right in that direction. You get specifically this alkene geometry. You do not get the other alkene geometry, which would be that, not formed. That's technically a diastereomer of that alkene. It's just a different geometric isomer, if you remember our isomers unit. Why do we only get this one? Well, because we are orienting that bromine and that hydrogen in an anti-arrangement, and we're getting the Zaitsev product. How could I get this? Well, I think I would have to change the stereochemistry of one of these spots. So a specific diastereomer in the starting material translates to stereochemistry in the product. Okay, so let's figure out some of these other products. B, we have, again, an E2, and I'm going to draw in the beta hydrogens. There is one down there on the tertiary carbon, and then we've got 2 others at the top of the ring. And I'm going to find the anti-hydrogen to this bromine. There's only one. It's that one up there. So our product, remember this is common in cyclic cases, is to put a pi bond in between those 2 carbons, and then our methyl along for the ride. If you want to draw your curved arrows, you certainly can. Draw an arrow from the ethoxide to the H. The CH bond breaks to become a carbon-carbon pi bond, and the carbon-bromine bond shows it leaving. How about C? Again, we have another small base. We have a very crowded molecule here. All the beta positions have been drawn in. If you don't recognize what that D is, you can make a note. That is a deuterium, which is just the second most common isotope of hydrogen. Instead of H1, it's H2. So it has 1 proton, but also 1 neutron. And we use these to figure out mechanistic properties and consequences of reactions. This is one way to sort of prove the anti-restriction of the E2 reaction. So which hydrogen is anti to the bromine? Let's just start with that. We're restricted to a ring here. It's actually the deuterium. Deuterium chemically behaves just like hydrogen, but we can track it using spectroscopic methods. So what's our product look like? Well, we have our 6-membered ring. We still have this methyl up here. If you want to, you could draw that other hydrogen. It's implied, so you don't have to draw that hydrogen in. We have a new double bond here, and then we have H's on those carbons. Notice, by the way, when you're drawing these things, you do not draw this with direction coming off of an alkene. I did it up there where I have an sp3 carbon, but it would be nonsense to draw a hydrogen like that with a dashed line coming off of that type of carbon. That's sp2. It's planar. So you never want to put dashed lines coming off of an sp2 planar carbon. So that's correct. And I would actually argue it's nicer to just clean this up and make it less crowded to draw. Just leave the pi bond and draw the methyl stereocenter and leave it as is. Okay, so let's do a few more, and then we'll practice. More E2s. First thing, find the beta hydrogens. There's one right there. Luckily, this molecule is already oriented in a conformation where the bromine and the beta H are anti, so the product I get has an alkene in between those 2 positions, and and I have a methyl coming off of that position. Again, not showing any more direction to that methyl. If you put a bold methyl there, it's not wrong, but nobody does it because it doesn't really show that you understand the geometry of the carbon that it's attached to. So draw your structures more accurately. You will impress people later on as you continue to speak this language. What if this wasn't anti to each other? Well, then I'd have to rotate around this carbon-carbon bond. That means the phenols, that's what pH stands for, the phenols would be pointing on the same side of the alkene as opposed to on opposite sides. Right below that, again, we've got beta hydrogens. I've got several of them. I've got one right there. I've got 3 more out here. This is a big, bulky base. Big base. Butoxide. There's really only a few you should look out for: butoxide, isopropoxide, and LDA. There are certainly others, but those are the 3 most common ones I think you'll see. So the big base means we're going to get the non-Zaitsev, and that means we're going to take away one of the more abundant hydrogens and the bromine. So the anti-restriction doesn't even matter here because I have more than enough types. So I'll get my carbon chain, 2, 4, 6, and 7. I have this existing methyl stereocenter that's just along for the ride, and I have a very simple monosubstituted alkene at the end of that carbon chain. Okay, so one more. We've got small base, so you get the Zaitsev. Find your beta H's. There's one right there. There's 3 others over here. Small base means I'm going to lose the less abundant H and the bromine. Is that anti or syn to the bromine? I drew it anti. Well, if it's not, you could rotate around that carbon bond and notice it's not a stereocenter there. Those are just 2 ethyl groups. So there's no possibility of different alkene geometries here like we saw in the past. You would get that. Notice I'm always just drawing an alkene in between the 2 carbons where the H and the bromine used to be. That's what your product looks like. Okay, there's a lot more practice on the back. The point is, look for things that are good nucleophiles as opposed to good bases. Notice that in this case, every single base was an oxygen anion. That's how you know if it's an E2. On the back page, you weren't told if it's an SN2 or E2. You have to try to figure it out. Good luck.